Welcome to Chapter 11, which is about water and it as a resource as well as pollution. And this is just a beast of a topic because water is one of the most precious and most important resources for humans on Earth. So we're going to talk about where does our water come from? How do we use water? Where and why do water shortages occur? How do we increase water supplies? What are costs associated with those methods of increasing water supply? How do we conserve water? What is water pollution? What are the sources of water pollution? What are the effects of water pollution? We're going to talk about why sewage treatment and clean water are important in developing countries. And we'll also talk about how we control water pollution. So we're going to pull in a little bit of the laws that are associated with water as well. As you probably are already aware at this point in your life, water is essential for life. There are so many different things in your body that require water. If you think back to some of our earlier chapters, we talked about water being a polar molecule and having a lot of special properties because of that. It is a universal solvent. Water can dissolve nutrients, it can distribute them to the cells, it also helps to regulate body temperature, it supports your structures, helps to remove waste products from the body. 60% of your body is made up of water. You know that you can survive weeks without food, but only a couple days without water. Because of this and because of how vitally important water is for the body, we tend to hold it in high esteem, but also because we have water coming out of our faucets, we maybe don't tend to think about water being in a shortage because of where we are. Water is needed for agriculture, which we talked a lot about in Chapter 7 with food and agriculture, industry, transportation. There's a lot of human uses. We interact with water on a daily basis. However, clean fresh water is one of the most vital resources, and I did hear a lot of people say in their discussions that water is potentially one of the best commodities that we have and one of the most important resources that we have to protect. There are worsening water shortages that are happening not only in cities but also in agricultural land. It's not only happening in the US, but it's also happening all over the world. For instance, in India, the Ganges River plain has groundwater levels that have declined 30 centimeters in just a decade, and I know that doesn't sound like a lot, but that is huge considering that their population is up to about 500 million people in that region. Military analysts are anticipating that rather than fighting wars over oil resources, that water shortage are going to become the focus of wars and refugee crises also. So it's really important for us as students to understand how water resources are distributed and also why they're changing so that we can help to find some better strategies to protect water as a resource. All right, so something that's important to start off with when we talk about water resources is withdrawals of water. And so this is a way when you take water out, you're reducing the water storage. And this water storage comes from some of the world's most important aquifers. So that's a big storage of water. And a lot of these are also coming from places that are politically tense regions. So the way we get this data is we have a satellite from NASA. It's called the Gravity Recovery and Climate Experience, or GRACE for short. It's cute. And what these satellites do is they're able to measure changes in the mass and specifically the water content of the land surface. So they're able to take real-time data regarding the aquifers, and are they being replenished, or are we taking so much out that the aquifer water amount is actually decreasing. So what we're looking at this graph, and this is a little tricky to see at first, is this 0 point is kind of, think of it like your baseline. And so this is where the aquifer should be at, and either you are increasing or you're going above the amount the aquifer is holding as of 2002, or you're going to see a line start to dip below that and you're seeing withdrawal, so it's decreasing in the amount of water that's in there. Specifically looking at our green line, this is showing the North China Plain. We see that it had a peak year somewhere around about 2004, halfway through about 2005, where we had a surplus in the aquifer. There was a lot of water in there. And then between 2004 and roughly 2014, we see a steady decline in that aquifer. So we are actually dipping below the baseline. So we're taking out more water than is being replenished via rain or any other type of precipitation. And if you look at the other regions that are included on this map, there's California Central Valley, Ogallala High Plains, northwestern India, the Middle East. The general trend is a decrease. We see all of these lines between about 2002, when we first started collecting data from GRACE. We see this downward trend. So we're actually withdrawing. We're taking more water out of these aquifers than the precipitation is able to put back into this water storage. To understand water as a resource, we have to understand how water is distributed across the globe. And to understand that, we have to have a little bit of an understanding of the hydrologic cycle. So, as you can imagine, water is moving continuously through the environment. The sun is driving a lot of the movement of water through the environment. So as the sun heats up water on the Earth's surface, that liquid water turns to a gas. It evaporates into the atmosphere. And as that gaseous water starts to cool, it will condense and turn into rain or dew or fog, or if it's cold enough, it'll turn into solid snow or ice, and it will fall back to the ground. We call any of that liquid or solid water that's falling back to the ground, we call that precipitation. So we have a cycle of it being evaporated into the atmosphere and then redistributed back on the surface of the Earth through precipitation. That really only covers the abiotic portion of the hydrologic cycle, and that's usually what we think of, but there is a biotic portion of that as well. So animals and plants are also taking up water, and so water, therefore, as part of the hydrologic cycle, is passing through organisms as well. So I think people are easier to imagine. We know that we drink water, we take water in, it passes through us, it's excreted. But plants play a really big role in the hydrologic cycle as well. So they have a lot of water passing through them, and they actually will change an environment based on how much water is moving through them. So plants are able to take up moisture from the soil through their roots, and that liquid moisture, the water, is going to move through their xylem. And one of two things can happen. Either you have the water that's landed on the plant, it can be heated and evaporated off, and that's just evaporation. Or the water that goes up through the roots is going to leave the plant through a little tiny pore in the bottom side of the leaf called the stomata. So when the stomata is open, water is pulled through the xylem and out through the pore, where it will evaporate into the atmosphere. That, when it leaves through the stomata, that's called transpiration. So plants have two different things going on. They have transpiration, loss of water through the pore, and they also have evaporation, loss of water from their surface. When you combine the two terms, it's evapotranspiration. That can change the local climates a little bit, depending on what types of plants you have or how much moisture you have there as well. So we talked about movement of water abiotically and biotically, and we know that that is driven by solar energy. What is interesting, and I think obvious after we say it, is that water can be picked up in one location of the Earth, and through the hydrologic cycle, it can actually be precipitated in a whole nother location. And so this really affects the climates and the biomes that we see across the globe. This image that we're looking at right now shows us that the areas of highest precipitation, this darker blue color, is right along the equator in the tropics. So we know that there's a lot more precipitation there. There's a lot more moisture coming from the atmosphere that's condensed and landed back on the Earth. Right above that, though, interestingly, we see a lot more deserts. So water is being picked up or evaporated from these deserts and being deposited down at the equator in another location. So the distribution is not equal across the Earth. And this presents all kinds of interesting climates. Here in North America, we know that just depending on what side of the mountain you're on, this can affect your hydrologic cycle. The leeward or downwind side of the mountain tends to be the side that's depleted of moisture. For example, I like to talk about Hawaii. I wish I were in Hawaii. I mean, we see this in the springs, but in Hawaii, the windward side of one particular mountain has an annual rainfall of 1,200 centimeters. That's 460 inches. That's a lot. But the leeward side, the side that's depleted of moisture, only has about 46 centimeters or 18 inches of rainfall. So depending on which side you are, that's really going to affect your hydrologic cycle and your distribution of water. All right, so let's look at the distribution of freshwater versus saltwater in terms of the hydrologic cycle. So your distribution of water is described in terms of interacting compartments in which the water resides. So a compartment could be water tied up in the ocean versus on land, water tied up in a snowfield or a glacier versus being in the ground or an aquifer. So that's what we mean by compartments. And your book uses the term residence time as being the amount of time that water stays in its particular compartment. So keep in mind that a residence time can be very short, it can be very brief, or it could be a very, very, very long time that it stays in that compartment. It really depends on which compartment it's in. For example, a water molecule that's in the ocean will usually stay in the ocean for about 3,000 years. That's an incredibly long residence time for a molecule of water, and that's just an average. As you know, nearly all of the world's water is in oceans, and about only 0.02% of the world's water is in a form that is accessible to us. So it's not salt water, it's fresh water and to other organisms. So I really like this diagram because it puts into perspective our water situation. So notice in this first one, all water can be divided into two categories. 97.6% is going to be found in the oceans. Remember, that's not accessible to us because of the salt content, and 2.4% is freshwater. So if we were to take this little tiny red wedge and we increase it, all of that 2.4%, 87.2% is tied up in ice and snow. This is not readily accessible water for us. I mean, we could heat it, but it's not going anywhere. It's not evaporating. It's not joining into the hydrologic cycle. It's kind of stuck in its compartment. 12% of that is groundwater, and 0.8% of that is fresh surface water. Of this fresh surface water, so that's what's accessible to us, again, they break it down further. So 45.7% of the 0.8% of the 2.4%, it's like Inception, is in freshwater lakes and reservoirs. So it's in a stored body of water on the surface. 23% is in the soil. It's not accessible to us. It's good for plants. 23% is in plants and animals, so it's kind of tied up in the living component. 4% in the atmosphere, and then the remainder is in wetlands, rivers, and streams. So we really, if you think about all the water that we have, the water that we can use is in such a small percentage and proportion, which is why it becomes one of the most precious resources. So we talked about this on the last slide, but let's go into that just a little more to drive home the point that we don't have much fresh water on the surface of the earth, and what we have is not always accessible to us. So as we said before, of the 2.4% of water that is fresh, 90% of that is tied up in the glaciers, ice caps, and snowfields. So that's not something that's readily accessible for us, I guess, unless we're just standing there with our ice pick, picking that off and heating up that water. The ice to become water. So most of the ice is located in Antarctica, Greenland, and the floating ice cap in the Arctic. Alpine glaciers and snowfields will also supply water to billions of people across the globe. I do want to talk specifically about the Rocky Mountains. That in the Rocky Mountains on the western slope, that snowpack, the winter snowpack that we see on the western slope of the Rocky Mountains, provides about 75% of the flow that we see in the Colorado River. There's an interesting case study at the beginning of the chapter if you're more interested in that. We do know, though, that drought conditions have reduced snowfall and runoff in the western U.S., and we're expecting that with global warming and climate change, that we are going to see a continuing shrinking of those glaciers and snowfields all over the globe. For instance, Tibetan glaciers, which are the source of 6 of the world's largest rivers, This supplies water to about 3 billion people. Those glaciers are shrinking rapidly as a result of climate change. There are some predictions and some models that say these glaciers could vanish in a few decades, which is not very far away. This would bring, as you can imagine, enormous suffering and economic loss to that continent. Groundwater is going to be a large storage resource for water. So think of water as originating or being at the part of the hydrologic cycle where it is precipitating or falling back to the ground. Once that water falls back to the ground, it's got to go somewhere. So either it's going to run off the surface of the earth, or it's going to percolate or move into the layers of the soil and rock. And it's going to become groundwater, and this is going to make up the largest compartment of liquid fresh water that we have. Groundwater tends to go a lot deeper than we think of. When you think of an aquifer, you have to think of it being as very deep in the earth surface. The groundwater within 1 kilometer of the surface is more than 100 times the volume of all the freshwater lakes, rivers, and reservoirs combined. So this is an enormous amount of water that isn't necessarily accessible to us. So we said that this is about 1 kilometer below the surface. That's a significantly deep aquifer. It's pretty far down there, especially when you consider if you have a house that has a well, or you need to dig a well for your house, you're really only looking at digging a well that's going to be 10 meters to maybe a couple hundred meters deep. So this may not be tapping into the actual aquifer. You're not going to get down into the biggest reservoir, underground reservoir of water. I think your book has done a bang-up job of providing these images that really show us where water's going, where it ends up, and what everything looks like. So let's go back a little bit and remind ourselves about the above surface hydrologic cycle. So we know that the sun is shining down. Here's my red sun. And it's heating up water that's on the surface, and that can evaporate, okay, back up to the atmosphere from the soil. It can evaporate from bodies of water, and it can rejoin the hydrologic cycle in the atmosphere. It can also come out of plants, come out of those little leaf pores, those stomata, in the form of transpiration. So we have water entering the atmosphere through transpiration and evaporation. But then when it falls back down to the surface in the form of precipitation, some is going to fall on plants that can be right away evaporated, some is going to fall on the ground, which will again be evaporated. So any water that does not get transpirated by the plant and evaporated is going to be water that can potentially join the groundwater. All right, so once water is sitting on the ground, there are different layers of groundwater. There's different zones of that. The first right here is called our zone of aeration. Your plants are going to get moisture from a relatively shallow layer of soil. The zone of aeration, think of aerating or having gas in there, or allowing air to be in there, because this layer is going to have both water in there and it's also going to have air. I think it's hard for us to remember that plants need gases in their roots. They need water and they also need gas. There's a gas exchange going on in those roots. So the zone of aeration provides this. It's not completely saturated with water yet. Depending on the rainfall amount, the soil type, and also the surface topography, your zone of aeration may be just a few centimeters, or it can be many meters deep. It just really depends on the area. Lower soil layers where all soil pores are filled with water are going to be your zone of saturation. So going down a layer, we have our zone of saturation. Think of this as being saturated or filled with water. So there's this distinct line drawn in the sand between your zone of aeration, where you have some air and some water, and your zone of saturation, where you have all water. And the line that is drawn here is called your water table. So this is the top of the zone of saturation. It is that little tiny portion between the zone of aeration and between the zone of saturation that's going to supply most wells. All right, so we've talked about groundwater storage, but what we haven't talked about is how we get that groundwater storage. We've been using the term aquifer a bunch, but we haven't really talked about what that means. So if you have a geological layer that contains water, we consider that to be an aquifer. Aquifers are going to have porous layers of sand or gravel. It could be cracked or porous rock, and that's going to allow water to penetrate or to flow through into that aquifer, that groundwater storage area. Below your aquifer, you're going to have these layers of impermeable rock, or it could be clay, and this keeps water from seeping out the bottom of the aquifer. So water will come in through what's called a recharge zone. This is where surface water is going to begin to filter through that porous layer of sand, gravel, cracked or porous rock, and it enters the aquifer, and it can't go any lower because we have that layer of clay. So what happens is typically you're going to see water, instead of seeping downward because it's blocked by that impenetrable layer, you're going to see water flowing horizontally until you have, say, an opening, say such as a stream, and water is going to leave the aquifer through that. Sometimes we get an impenetrable layer or an impermeable layer above an aquifer. When you get that layer that is impermeable to water and it's above your groundwater, your aquifer, you're going to get pressure develop in that aquifer. And should you get, say, a little hole or a crack in your rock, you're going to wind up with water, pressurized water, spewing to the surface. We call these springs or artesian wells. That's actually how we get our spring water that is all over Manitou. If you ever get a chance to go down there, they have some springs with water just coming straight out of the ground. It's due to that impenetrable layer creating pressure and driving the water upward to the surface. You can drink those at your own risk. It might be something kind of fun to check out. So the recharge zones tend to be tricky places. If you have road or house construction or water use at the surface, this can further slow the recharge or water flowing back into the aquifer. So we know we have a lot of construction going on. Water is not able to recharge at those zones. Also, a recharge zone is a place where contaminants can enter your aquifer. And that's something that we have to be really careful about anytime we have a recharge zone, making sure that we're protecting it from contaminants, because your whole aquifer is going to go if you get contamination into your recharge zone. So we just talked about how slow aquifers recharge, or how slowly they refill with groundwater storage. Now we're going to talk about rivers, lakes, and wetlands, which cycle very quickly. They're able to charge a lot quicker than, say, an aquifer. Rivers contain a relatively small amount of water at any time. Just to give you an example, most rivers would begin to dry up in days or weeks if they were not constantly recharged by precipitation or snowmelt or groundwater seepage. We do compare the size of rivers in terms of their discharge. So when we say discharge, we are talking about the amount of water that passes a fixed point in a given amount of time. The 16 largest rivers in the world are going to carry nearly half of all the surface runoff on Earth, and a large fraction of that occurs in the Amazon alone. This Amazon is going to carry nearly as much water as the next 7 biggest rivers together, which is an amazing amount of water. Lakes contain nearly 100 times as much water as all rivers and streams combined, but a lot of the water is only in a few of the world's largest lakes, such as the Great Lakes here in North America, the Great Rift Lakes of Africa. So while there's a lot in there, the distribution of these lakes is very select. They're only in a couple places. Rounding us out for surface water would be wetlands, bogs, swamps, wet meadows, and marshes. Typically, these are really vital for an environment, but they go underappreciated or unappreciated at all when we talk about the hydrologic cycle. The springs here in Colorado Springs, we tend to have a lot of wetlands area. It used to be when we saw a piece of land that had a wetland, we would drain the marsh, we'd drain the wetland, fill it in with dirt, and we'd build right on top of it. And one of the issues that we see when you're to drain that area is all those plants in the wetland are doing a bunch of different things. First and foremost, they are stabilizing the soil. So their roots are keeping that soil intact so it doesn't just wash away in one big rainstorm. Also, they're holding back surface runoff. So when water comes into the wetland, it is stopped by all those plants and all that vegetation, and that allows the water to slow down and have time to seep and penetrate back down into the aquifer. So that's a way to recharge it. Here in the Springs, if you, we do a land trade. So if you were to take and build on a wetland, it is expected that you will purchase another area for conservation for a wetland. So we're trying to do land swaps for that. If you ever get a chance to go down to Fountain Creek Park, that is a great wetland to observe that has been intact, and it continues to grow in size as we do land swaps. So referring back to that little pie chart that we saw, the small portion of freshwater is smaller, smaller, smaller. The smallest portion in the hydrologic cycle that holds freshwater is going to be the atmosphere. So this is one of the smallest compartments. It contains only 0.001% of the total water supply, but it's one of the most important mechanisms for redistributing water around the world. So when we think of a water molecule evaporating off the surface of the earth and becoming its gaseous form, that water molecule can reside in the atmosphere for about 10 days on average before it's going to condense and fall back to the earth in the form of precipitation. Some water can evaporate and fall back to the earth within a matter of hours, just depending on what conditions the atmosphere has that particular day. Water can also travel great distances. It can travel halfway around the world before it falls. It can replenish surface streams. So if it's not able to penetrate into the soil and become part of the aquifer, it can become surface runoff into streams and eventually lakes and rivers. Or it can penetrate the ground and become part of the groundwater reserves in an aquifer.